Say we have a uniform beam 2.2 meters long with a mass 25 kilograms. It is mounted by a small hinge on a wall, and the beam is held in a horizontal position by a cable that makes an angle of 30 degrees to the horizontal. The beam supports a sign of a mass 28 kilograms suspended from its end. Determine the components of the force H that the smooth hinge exerts on the beam and the tension of the supporting cable. So here we have a cable being used, and the thing to keep in mind about a cable or a cord of some type is that it can only support forces along its length. This is because any forces that are acting on the cable perpendicular to it would result in the cable bending at that point of the force. So we draw the tension force in a direction that exactly follows the cable. The cable makes a 30-degree angle with the horizontal, so the tension force will have X and Y components with it. Now we also have forces acting on this hinge. If you think about what is happening with this hinge, there's a force being pulled over to the right and a force acting up in the opposite direction as the weight that's pulling down on the hinge. So now we have a force diagram for the beam that shows not only all the forces acting on it, but also a guess for the forces acting on the hinge. We are looking for the X and Y components of this force as well as the tension force of the cable, so we actually have three unknowns. So let's start with our sum equations. Now we have angles involved, so we need to consider that the forces might have components to them. There are four forces acting on our system: the Y component of the tension of the cable, the Y component acting on the hinge, the weight of the sign, and the weight of the beam. Since the beam is not moving, all of these forces acting together will be zero. If up is positive, then the Y component of the tension and the Y component of the hinge are both acting in the positive direction. The weight of the sign and the weight of the beam, then, would both be acting in the negative direction. In the horizontal direction, we only have two forces acting. Choosing right as positive, then the X component of the force on the hinge would be positive, while the X component of the tension force would be negative. Now let's look at our sum torque equation. A nice place to choose for our axis point would be the end of the cable where the sign is pulling down on the beam. This would make the lever arm for the tension force, gravity force, and the X component of the hinge all zero. And again, we are going to say that any torque that causes a counterclockwise rotation is a positive torque. The weight of the beam is causing a positive torque, but the hinge is a little bit more difficult to immediately see. The vertical component of the hinge is happening because of the weight of the sign, so it is acting in the up direction. So the vertical force on the hinge would actually act to cause a negative torque. Let's just start with torque, mostly because there seems to be fewer variables involved. The torque on the hinge adding to the torque on the beam is equal to 0. We can write that out as the Y component of each force times the distance from our pivot point. Now why would we need to use only the Y component? If you think about how a torque acts to rotation on an object, you need to apply a perpendicular force. Remember that the X component acts along the lever arm and it does not contribute to the torque. This is actually nice because the Y component of our hinge is one of our unknowns, so we can rearrange and solve for that. From our problem, we know that the hinge is 2.20 meters away from where the cable attaches. Since we assumed that is our pivot point, then R for the hinge is 2.20 meters. R for the beam itself is 1.10 since the center of mass is at the halfway point. The force of the beam is the weight of the beam, which is its mass, of 25 kilograms times 9.8 newtons per kilogram. So solving for the Y component of the force of our hinge, we find it to be 123 newtons. So there's one of our unknowns. We still need to find the tension force and the X force component of the hinge. Well, let's look at our force equations for a minute. It looks like the two X components are equal and opposite. So if we could find one of those, we could find the other. When we look at our Y equation, we can see that we have the hinge's Y component now. We can also find the force of the sign and the force of the beam. So it looks like we can find the force of gravity acting on both of those, and that would lead us to find the tension's Y component. So let's see if we have all of this information. The Y component of the tension will be equal to the negative Y component of the hinge, which we just found, plus the weight of the sign, plus the weight of the beam. So plugging in all those numbers, we find that the Y component of the tension force is equal to 396 newtons. At first glance, this might not appear to help us a whole lot, but don't forget that we know the angle involved with the tension force. So if we know one component, we can find the other. So to find the x component of the tension force, we just take the y component divided by the tangent of the 30-degree angle. This gives us a tension force of 686 newtons. Now this is going to let us find a couple things. First, we know from our sum force equation that the x component of the hinge will be equal to the x component of the tension. So the x component for the hinge is 686 newtons. And finally, since we know the x component and the y component of our tension force, we can now find the tension force itself. We haven't used Pythagorean in a while, and that's a nice one to use because it's so simple. So if we take our x component of the tension and the y component of the tension, both of them squared, and add them together and square root them, we find the force of tension is 792 newtons. So that's it. What a fun problem. Now note that this is just one way to solve the problem. The key is to properly define the forces and torques within your chosen system and keep the positive and negative values straight.